Hello friends, in this lecture we are going to discuss how to solve problems on principal traces by analytical and graphical method whenever oblique plane is not given. So we'll take review of the formulae. Already we discussed in a lecture first. So in this principal stresses we consider 2D element and traces acting on the 2D element. Normal traces and shear traces. This is normal trace, this is normal trace, and this is the shear trace. And for derivation purpose we consider triangular element from this 2D element, that is AB element. Here we have drawn the free body diagram. We have shown forces which are acting on this triangular plane. This 2D element is in equilibrium condition, so due to that this triangular element is also in equilibrium conditions. Means we can apply equilibrium condition summation fx equal to 0, summation fy equal to 0, and by applying this equation we get some formulae. First, sigma n, that is normal trace, equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta plus tau sin 2 theta. Second formula is sigma t, that is tangential trace, equal to sigma x minus sigma y by 2 into sin 2 theta minus tau cos 2 theta. Third formula is resultant trace, that is sigma r, equal to under root sigma n square plus sigma t square. Fourth formula, tan phi, that is phi means angle of obliquity, equal to sigma t by sigma n. Phi is the angle between the resultant trace and normal trace. Then fifth formula, tan 2 theta p1, it shows that orientation of a principal plane, or we can say location of principal plane with respect to reference plane, either vertical plane or horizontal plane. That formula equal to 2 tau divided by sigma x minus sigma y. There are the two principal planes. One is a major principal plane and another is a minor principal plane. So this formula is for minor principal plane, theta p2 equal to 90 plus theta p1. Then also we need to calculate or to find out orientation of a maximum shear trace with respect to reference plane. The formula for that, tan 2 theta s1 equal to minus in a bracket sigma x minus sigma y by 2. There are two maximum shear trace plane, so we'll get two locations. So theta s2 equal to maximum stress orientation equal to theta s1 plus 90 degree. The next formula is for major principal plane. It is denoted by sigma n1 or sigma 1 equal to sigma x plus sigma y by 2 plus under root sigma x minus sigma y by 2 bracket square plus tau square. Next formula is sigma n2, or we can say sigma 2, that is minor principal trace, equal to sigma x plus sigma y by 2 minus under root sigma x minus sigma y by 2 bracket square plus tau square. And last formula is tau max, that is maximum shear stress equal to sigma 1 minus sigma 2 by 2. Now we'll solve the problem. First we'll solve by analytical method. Now this is the given problem. Stressed element in a machine component is subjected to 185 MPa tensile stress, 55 MPa compressive stress and 75 MPa shear stress clockwise on a x face. Compute the values and orientation of a principal stresses, means we need to find out major principal stress and minor principal stress, and maximum shear stress using graphical and analytical method. So first we'll write the given data. So according to statement, sigma x equal to 185 MPa, sorry, here I have written 185 MPa, and stress is given tensile. So according to sign convention, we take tensile forces, tensile stresses positive, sigma y 55 MPa, but nature of that force is that stress is a compressive, so here we have taken negative. Tau equal to 75 MPa, negative, because 75 mm stress acting in a clockwise direction on x face, means on a vertical face. Now according to the problem statement, we need to find out principal stresses and its orientation, means we need to find out major principal stress, that is sigma 1, minor principal stress, that is sigma 2 or sigma n2, maximum shear stress, that is tau max, principal plane orientation, that is theta p1, or we can say principal plane location, then another principal plane location, that is minor principal plane location, then maximum shear stress and location of maximum shear stress with respect to reference plane, that is vertical plane, theta s1 and theta s2. Now we'll solve it by analytical method first. So first convert the statement into diagram. So this is the 2D element, two mutual perpendicular traces, normal traces acting on the plane, one in x direction, another in y direction. So we have taken sigma x equal to 185 MPa positive, sigma y equal to minus 55 MPa. Due to compressive nature, we have shown here downward direction, and 75 MPa shear stress on x face. This is the x face, or we can say vertical plane is the x face. It is acting in a clockwise direction. According to sign convention, clockwise direction we treat tau negative, but on a horizontal face this is in an anti-clockwise direction, and that is positive. And this is the second type of problem. In this problem, angle of oblique plane, or we can say inclined plane, is not given with respect to vertical plane. So this is the given data. Sigma n equal to sigma n1 equal to sigma 1, that is major principal stress. So we know the formula. Sigma 1 equal to sigma x plus sigma y by 2 plus under root sigma x minus sigma y by 2 bracket square plus tau square. So according to given data, value of sigma x equal to 185 MPa, sigma y equal to minus 55 MPa, and tau equal to minus 75 MPa. Just put the value of sigma x, sigma y in this equation, we'll get the value of major principal stress. It is denoted by sigma n1 and sigma 1. So in this way we will get the answer for the sigma 1 equal to 206.5 MPa. Now second, we need to find out minor principal stress. For that, formula is sigma n2 equal to sigma 2 equal to sigma x plus sigma y by 2 minus under root sigma x minus sigma y by 2 bracket square plus tau square. Just put the value of sigma x, sigma y and tau, will get the value of sigma 2. Here we get the value of sigma 2, that is minus 76.5 MPa. Now third, we need to find out the principal plane orientation, or we can say location of principal plane. There are the two principal planes, one is a major principal plane and another is a minor principal plane. So here first tan to theta p1 we are using for to find out the major principal plane orientation. The formula is for that 2 tau divided by sigma x minus sigma y. Now we know the values, just put the values, we'll get the value for the theta p1, that angle is minus 16 degree. Next, minor principal plane orientation, that is equal to theta p2 equal to 90 plus theta p1. So already we got the value of theta p1, that is minus 16 degree. So in this way we will get the value of minor principal plane location, that is at 74 degree with a reference plane. Then as per given statement, we need to find out the maximum shear stress orientation or location. Formula for that is tan 2 theta s1 equal to minus in the bracket sigma x minus sigma by 2 tau. Similar to maximum principal plane, minor principal plane, maximum, there are the two maximum shear stress plane. So to find out the another maximum shear stress plane, formula is theta s1 plus 90. So in this way we get the value for theta s1 and theta s2. Now next entity, according to statement, we need to find out tau max, that is maximum shear stress. Formula for tau max is sigma 1 minus sigma 2 by 2, or we can say major principal stress minus minor principal stress by 2. So already we found the value of major principal stress, that is 206 minus 75 divided by 2. So in this way we got the value of tau max, that is 141.5 MPa. Now we'll solve the same problem by graphical method, or we can say by Mohr circle method. Again, sign convention is important for graphical method. Tensile stresses should be treat positive, compressive stresses should treat negative, anti-clockwise shear on a vertical face treat positive, clockwise shear on a vertical face negative, clockwise rotation positive, anti-clockwise rotation negative. And one note is important, angle between any two plane on a Mohr circle is twice that of a actual angle. Now for our problem, sigma x is positive according to sign convention, sigma y is negative, tau on a vertical face is clockwise, so tau is negative, but for horizontal face tau is a positive. So this vertical plane is a x plane and this is horizontal plane is a y plane. So once again we'll draw the figure for the problem. In x direction 185 MPa, in y direction minus 55 MPa, and tau minus 75 on a vertical face and positive 75 on a horizontal face. Now we need to select the scale. So for this particular problem we are going to select the scale 1:2, means 1 mm equal to 2 MPa. Means if we want to plot 185 MPa, we are going to take a distance equal to 92.5 instead of 185. Instead of 75 we are going to take a distance 37.5. So meaning of this scale is 1 mm equal to 2 MPa. So first draw the x-axis. We are going to plot normal traces on the x-axis. Then draw vertical axis. We are going to plot shear traces on this vertical axis. Then plot a point from O, that OA distance equal to sigma x, that is 185, but we are using the scale 1:2, so we are taking distance equal to 185 by 2, that is 92.5. This distance is 92.5. Then plot point B. Now this B point means y direction trace. Now this trace is a negative, so we need to draw distance behind the vertical axis, or we can see in a second quadrant, or on a negative x-axis, that OB distance equal to 27.5 because of scale. OB is a minus 27.5. It is sigma y distance. Then draw perpendicular from A point. This distance equal to tau. So tau is given minus 75. This is the tau positive. This is the tau negative. So tau value is negative on a vertical face. So from this A point we are going to plot tau distance below the x-axis, or we can say towards the negative y direction. So this AR distance equal to tau, and this A point indicating the vertical face. Similarly from B point also draw tau distance. Again that distance is equal to minus 75, but according to scale that distance is a 37.5. This distance is a tau distance, but we are plotting in a upward direction because on a horizontal face tau is in a clockwise direction. Then join this R to S, and for the intersection point give the name C, that is our center point for the Mohr circle. Then draw the Mohr circle with a radius equal to CS or CR. We can see this circle intersect to the x-axis at the right side. For the intersection point give the name P. That Mohr circle also intersect at the left side of the x-axis. For the intersection point give the name Q. Now this OP distance equal to major principal stress, that is sigma 1, and this OQ distance is known as a minor principal stress, it is sigma 2. Then draw perpendicular from this C point, C to M and C to N. This Cm indicating the tau max, Cn also indicating the tau max. This is the one maximum shear stress plane, this is another maximum shear stress plane. Now this angle is 2 theta p1, means angle of major principal plane with respect to reference plane. Major principal plane means this OP is our major principal stress, because at point P value of tau is 0. Whenever we get the value of tau is 0, that plane will be the maximum principal stress, or we can say that plane is a major principal plane. So location of major principal plane from the reference plane, this R point is our, or we can say CR is a reference line, reference plane, because this R point indicating the vertical plane. Here coordinate of this plane is 185 and minus 75. So this CR is a reference plane. We are measuring major principal plane angle in an anti-clockwise direction. So this angle will be negative. Now angle of maximum shear stress plane. Now this is the maximum shear stress Cn or Cm. Now this we are measuring this angle with respect to again vertical plane, again from reference plane, but we are measuring this angle in a clockwise direction, so we'll consider it is positive. That angle is 2 theta s1. And then location of another major principal plane. This is another major principal plane. Here at a point Q, again we get the value of tau equal to 0. At this point we get the tau value 0. So we can say this OQ plane is a minor principal plane. If we compare with this OP is a larger value or greater value compared to the OQ. So this OP is a major principal stress, major principal plane, or OQ is a minor principal stress, minor principal plane. So angle from the reference plane we can measure in this way, that RCQ angle. So this angle, and we measuring this angle in a clockwise direction, so this angle will be positive, this angle. Now this X plane, this is the X plane, this R point indicating the X plane. This is not a point, actually this is the vertical plane, and this S is also horizontal plane. Coordinate of the horizontal plane is, sorry, here I have written wrong. Here value is minus 55 and minus 75. Here value is 185 and minus 75. Now to get the value of major principal stress, we need to measure distance OP and then multiply by the scale factor. Our scale factor is 1:2, so multiply by 2. So this distance OP distance is 102.5 mm, multiply by scale factor, that is 2. So in this way we will get 205 MPa major principal stress. Sigma 2 minor principal stress. So this OQ distance is minor principal stress. We need to measure this distance by scale. So I got this distance minus 37.5, but we need to multiply by scale factor, that is 2. So in this way we will get sigma 2 equal to 75 MPa. Value of tau max cm or cn, that radius equal to the tau max. Cm into scale 70. I measured this distance equal to 70 into scale factor 2. So in this way we will get tau max equal to 140 MPa. Now location of major principal plane, minor principal plane. Theta P1, that is angle RCP. We measure this from this reference plane, but in a anticlockwise direction. For anticlockwise direction we take negative sign. So theta P1 equal to RCP divided by 2. Theta P2, location of another principal plane. This is another principal plane. We are measuring angle from the reference plane again. So cone RCQ divided by 2, that angle is 75 degree. Then theta S1, maximum shear stress plane location. This is the maximum shear stress. Again we measured from the reference plane, but we measured in a clockwise direction. At angle RCN divided by 2 equal to 28 degree. Divided by 2 because in a Mohr circle we always taking twice the angle. So to get actual angle we need to divide it by 2. Then theta S2, this is another maximum shear stress plane. Now we measure this angle in a anti-clockwise direction, this angle. So this angle is a minus 61 degree. So in this way we learned how to solve the principal stress problem when angle of oblique plane is not given. Thank you.